Hello viewer, we are writing our BIOS bootloader for the operating system that we are writing, from scratch by the way. Today we are going to load the kernel ELVEN executable. So let's get cooking. So before we get started, I want to show you a few things that I did before I started the recording. I created this folder kernel here that has a beautiful kernel file. So our kernel executable for today would be this beautiful while loop. So it's just a stub or a placeholder for our actual kernel. I've created basically I copied the linker file that we had on our bootloader, and I've changed a few things. And I've created this make file here just so that we can output a kernel64.elf, which we will use as our kernel image. Right, so let's change a few other things. Here we have this kernel placeholder.txt here, and we can just get rid of this and change this to be our so kernel64.elf. Right, and with this I think we should have a working disk image after we finish loading it. I've also created this elf.h file. Since we are not going to go into the details of how the ELF format works, as we have, or I have already covered that to the extent that we need it in the Skillable video on ELF. So go take a look at that if you want to know more about the ELF format. However, we are going to see in detail how the format is used, how we are going to use the format to load our executable. Right, so what I have here is just a few structs and a few defines that are basically the values that the fields of this struct take, so we can just access them easier. So here I have the ELF64 header struct, which is basically the first thing that we have on top of any ELF file. And here we have so once we read this and we check that we have the correct ELF type, class, and machine version, and Indianness, and all that good stuff, we are going to start loading our program headers. And speaking of program headers, we have here our ELF64 program header struct that we are going to use. So this here wouldn't change, and I guess we can just go straight ahead to our main file. Oh, right. So here we finished loading the kernel file. We have the address of the memory that the kernel file occupies. So I guess we could create a function that we will call load kernel executable. And this one would take a kernel file, right? And this should return. So let me think about this. I guess we want to return a pointer to the entry point of our kernel. We'll see where this goes, but for now, this is what we're doing. Let me just forward declare this here. So load kernel executable. There we go. And this one takes a, I guess, void star to kernel. Should I call it kernel buffer or just kernel, I guess? Yeah, that looks pretty okay. And now we go down here. We create, wow, kernel executable takes a void star, kernel, yeah, just kernel. And here, what are we going to do? So what I want to do is I want to check. So here, step one. So let's think about this. I want to check the type of executable, right? Step two would be call the appropriate function to load it. And Yeah, I think that's pretty much it. Yeah, so let's do it. Right, so we want to check the type of executable and to identify elves, to identify elf files. We need to check we have these 3 magic bytes at the very start of the file. And what I did is I've just very conveniently created this define here that just combines the 4 bytes into just one D word just by shifting them around. And yeah, so what we'll do is we will just go over here and do if. So let's first do U32 pointer and call this kernel start, or should I call this elf start? And this will just cast U32 pointer our kernel in there, and here we're just going to deref elf start and check that this would be equal to elf magic. There we go. And I'll just check this. Yeah, of course, it's not imported yet. Cool. So let's include this. I think it's called alpha H. There we go. And if we go back here. All right, okay, so it's the correct thing. And it expands to the correct thing. Correct. Great. Right, so if we have this, then we should just return, I guess we can create a function called load elf, right? And I guess step 2 is this load elf here, so we can just get rid of this and get rid of this. And this basically lets us add, for example, PE or portable executable if we want to add that format afterwards. What we are going to do here is, since we basically have, we should enter one of the functions, loading functions, so we should just panic here if we couldn't choose one. Kernel not in the correct format, or should I say unknown kernel format, maybe something like this. And of course we are just going to spin here. Right, so now let's create void star load elf that takes our, of course this would need to take void star kernel for the moment, and I guess this one here needs kernel. So let's work on this now. So first thing we want to do is create elf64 header pointer, of course, which is our elf header, and this would be elf64 header star of kernel. Right. Right, so what we need to do now is do the checks for the different identification fields that we have. We know that the magic is correct because that's how we got to this function, so we don't need to check that. However, so if we just do something like this and go down here and see what we need to check. So we need to check class, which is 64 or 32 bits, data, which is the Indianness. Version, I don't think we need to check it, but yeah, so I will just check the class and data, I think. Right, so let's, so if, elf header ident, yeah, that's what I called it. And this is an array, and we can index it with this ident fields. So class, right, if this is equal, or yeah, maybe we should just check if they are different and just return some sort of error. Right, so if our ident class is not, so elf class 64 or, oops, or elf header ident of elf data. No, ident data is not, so we are expecting least significant bit or little indent. Right, if we have any of those, we basically just printf something like error unsupported elf. Should probably just split these, right? Yeah, should probably just split those. Okay, calm down. Right, something like this. And we can just do this. So error unsupported elf class. Something like this. And of course here we just spin. Right, so let me just copy these, put them here, and this one would be an DNS. There we go. Right. So now that we know that we have our correct NDNS and basically class, we need to check what kind of machine this was compiled for. So we can do that just by checking the so elf header machine field, and we expect this to be so what did I call it? Machine x64. Yep, this one. And if it's not the case, then we can just probably just go ahead and copy this somewhere here. Or elf file not compiled for x86-64. There we go. So now I think we are done with the checks that we want to do. So let me just go ahead and check if we need to do something else. We can always check the version, but it's pretty much useless. And we can also check the type just to make sure that it's an executable. Yeah, let's do that actually. So let's just copy this and do the check on the type. And of course, we expect type to be exec, since we want an executable. And so what are we going to do here? Yeah, I guess we can change this whole thing. Expected an executable file. Elf file. There we go. And with this, I think we can just go ahead and start doing our loading. So let's do that. So first thing, I guess, is we take note of our entry point. Point. This one would be elf header entry. Yep. And of course, here we need to get our program headers. So let's do something like this. PHDR. Star, of course, and this would be program headers, and this would be so elf64 PHDR. So we know that we have, so if I do this, we know that we have this program header offset, which is the offset from the start of the file to the first entry of the program headers. So that's what we are going to do. We're going to take the elf header, or maybe we can just take kernel, and we are going to add to that elf header dot program header offset. There we go. And with this, we should have our program headers. I guess this is a U64. Yeah, it's gonna complain, so let's just do this. And then we have that cast as a program header. Cool. Right, so now we are just going to loop over the program headers that we have. So U32 I goes to 0 and I is less than header dot program header count. We have count plus plus I. Yeah, just one I, please. And now we are going to basically get every header. So just create PHDR, just recreate a sort of instance here just for ease of use. Right, and this would be PHDR, just call it that. And we just take the program headers, and of course we take the ith element here. And of course here we check that the type, so PHDR dot type, we are expecting, we check that it's not, so prog type load, there we go. So if it's not the case, we again we'll need to print an error, because actually no, why would we do that? We just need to ignore it and continue. The error would be if we don't find any, but yeah, so for now let's just continue continue our loop. Right, so if we found one, if we go back here to program header, we can see that we have a so file size, mem size, and these two can be different, and we'll see the use of basically why we are specifying these two here. We have the offset, which is the actual location of the segment. And yeah, virtual address and physical address. I don't think we are going to use those right away. But yeah, let's continue then. So here, what we are going to do is we are going to, I guess we are going to take mem size, which would be our PHDR mem size. And we are also going to take, so here I'll just note something to do, add size check to avoid kernel being too big. Just put that there for later, because we might want to add a sanity check for our kernel so that we know when it gets a bit too big and we need to start splitting it up into modules. But for now, we will just think in terms of a single monolithic kernel file, kernel executable. Right, so next we want our load address. So we will try to, I guess, do something like this. Load address would be pm alloc, and we'll allocate the memory size, right? So memory size is mem size, and the type would be mmap. Actually, I want to create a new type called kernel kernel modules. Kernel module, yeah, looks good. And of course, we we'll go to, so it's over here that we've defined them. No, actually it's in boot info that we've defined them. So let's do this, call it kernel module. And of course this goes to 6. And here we do kernel module. That was pretty self-explanatory, I guess. Right, so let me just get rid of these things here. Right, so mem size here is a U64, and here we are just taking U32s. Yeah, so this is why we would need this check here. I guess I should get rid of this to do and just do the check. Right, so if mem size is bigger than let's say 64 megs. This is totally an arbitrary value that I just picked right now. And yeah, we'll see what we can do here. So let me just put this here first, and here we are going to do error kernel too big. Consider splitting it into modules. Of course, here we can just do this. There we go. Okay, so I guess we now need to define this megabytes. So what I'll need to do is, yeah, I don't have a better way to do this. So let me just do it here. I'll define byte to be, wait, no, not byte, kilobyte of x to be, there we go, x times 124. I'll define megabyte of x to be, so it'll be kilobyte of x. Yeah, there we go, times 124. And yeah, I don't need more than that, I think. It should be fine. Right, so now if we go to here, just check that this expands correctly. Yeah, it looks pretty good. It looks pretty good. Right, so if we have this, that means that the value can basically just get cast. We're not going to lose precision. And now we have allocated the basically memory for this segment here. So what we need to do now is basically, it's as easy as just copying it over. I guess we need to check this. Does this return a, I guess this returns a null pointer if it couldn't allocate memory. So if load address is null, yeah, we can just print something here again. Let me just bring this, put it here, and we can just change panic. Couldn't allocate. I guess we can just set the size there. Bytes of memory. And this would be mem size. Right. Okay, so now we know that we have a load address allocated somewhere. So we just need to basically mem copy our things. So destination would be load address. Source would be our right. So let's compute the source here. So void star segment would be a void star, of course. But here we are going to take our kernel, cast it to U64 kernel, and we are going to add to that the program header dot offset. Okay, it's not working with me. Offset, there we go. And with this, I think we should be okay. So yeah, load address here would be so segment as the source, and the length would be, of course, program header dot so file size. Right. So basically, file size is the size of the segment on the file, and memory size is the size that it should occupy in memory. What happens is that if we have a file size that's smaller than memory size, the opposite can never be true. So we cannot have a memory size that's smaller than a file size. But if we have a file size that's smaller than the memory size, that just means that the ELF format expects us to initialize the rest of the memory with zeros. So that's what we are going to do. And I guess this one here would just need to be cast to U32 because that's what we have as length. And of course, and this works because if memory size is not larger than 64 megabytes, then the file size wouldn't also be larger than 64, so we can cast it safely here. Take that, Rust devs. Right, so here we basically take the difference between the memory size and the file size, right? So PHDR file size. And this difference here is what we call BSS size. That's why basically when we have a BSS segment, it just means that it has a file size of 0 and a memory size of whatever the segments need to be. And it just gets initialized to zeros after we, because this memcopy would basically do nothing if file size is 0. And we just initialize it with zeros here. So let's do that. So if BSS size is not 0, that means that we need to do a bit of work. I guess we need to have a pointer to where it starts. So call it BSS start. And this would be the offset plus the so this would be the load address plus the file size, so plus the program header file size. Right, and with this we should just call memset. So memset, we already have it implemented from the last video. So here it takes the destination here would be BSS start. The character would be 0 and the length would be BSS size. There we go. So with this we have a working segment, and I guess BSS size we can also just safely cast it to U32. There we go. Right, so this is a bit of an issue because we still need to know. We saved the entry point, but we haven't saved the so U64 kernel start address. Yeah. So we haven't saved that, and what we need to do is if the kernel start address is still 0, we need to initialize it to our very first memory that we've allocated, so that we can afterwards do virtual mapping for this kernel. Because up till now we are still working with physical memory, and yeah, we'll need the physical address we loaded the kernel to be able to map it to virtual memory afterwards. So what we'll do here is I will just set kernel start. All right, hold on. Kernel start. There we go. Set this to load address. Yep. And I might also need to store. Yeah, this needs to be cast. Might also want to or need to store so U64 kernel size is what I'd like to call it. Right, and that's 0. So here we actually for every module that we have, we need to do kernel size plus equal the memory size that we have loaded for that module. Yeah, that looks fine. That looks fine for now. We'll probably, once we start doing virtual memory stuff, we'll probably come back here and change a few things. But for now, let's just do what we have to do. So return kernel, wait, what did I call it? Entry point, just entry point. Entry point, there you go. And of course, entry point here is a U64. I guess you can just cast it to be a pointer, right? So void star pointer. There we go. So that pretty much sums it up. Yeah, there we go. And so what I'll do is I'll just have these two commented out because we are not using them for now. This code too, but for sure we are going to need them. And yeah, let's compile this and see what we have. All right, so here we have a warning about an unused variable and an error for ELVEN MAGIC. So let's see what we can do about those. Right, so first of all, let's get rid of this warning. Loaded kernel executable to 0x %x instead of s. And of course we need to do this, and here would be entry point. Right. So that deals with the warning. And now if we go to ELF here, so we have this magic. Okay. Oh, okay, I see it. There's a bit of a. There we go. That should be much better. So let's rebuild this again. It looks pretty okay. Let's run it and see what we have. So we have unknown kernel format. Right. So it loaded the kernel file and it read the start of it, and it found these bytes here, which are not our expected bytes. So let's see why that is. So what are we doing wrong here? So we have the kernel file here. We are trying to read the first 4 bytes, and we are not reading the correct stuff. Right. And here we know that we have put our kernel 64.elf into the right thing. So I guess we could just go and check what our kernel 64.elf looks like, right? So if we do hexd build kernel 64.elf, yeah, probably should just do something like this. That's weird because we actually have the correct signature here. So why is it not doing the correct thing? Well, we have a bug here in our loading logic. So we've created this index here that basically points to where in our allocated buffer we are writing. So basically it's an offset from the start of the buffer, and we are never updating it. So that might be a bit of a problem, right? So let's do index plus equal, and we will take so fat fsinfo.bpb, and this would be sectors per cluster, and we multiply that by fat fsinfo.bbb.bytes per sector. Right, and if we do this, rebuild it, and let's run it and see. Okay, so this time we actually have our executable loading. We can see here that we have the magic bytes in Little Indian. So this would be elf with 7f as the first byte. And we can see that we have loaded our executable to some address here. This is the virtual address that the kernel wants to be at, and it's truncated. And with this, we have loaded our elf executable. Like and subscribe. There is a poll in the channel's community page for what we are going to do next once we finish the BIOS bootloader. Until then, I'll see ya. Take care. Bye.